All right, again, noise. It's all your fault, okay? I'm just going to label it that. Even though the board should reject all noise, it doesn't. In fact, it doesn't reject a lot of noise. And by design, because you get to solder, what was it, like 300 joints? If you want to solder 2,000 or 3,000 joints, we can put so much noise filtering on a board that, which is half the board, would be protection everywhere. But then again, you want to spend the next 3 or 4 days assembling a MegaSquirt. So there are things you can do to reduce noise, and there are little mods you can do to the board on a V3 board that help reduce it as well. And we're gonna change the V3 board, tweak it a bit for some of these noise mods that everybody out here has it. I'm not showing you all of them, only showing you a few of them. Everybody has their own favorite one. Maybe at the end people can say, hey, I did this. I painted the box purple and it got rid of the noise. Or there are things you can do. You know, you maybe use a witch doctor type of dance over it. They all help. So you can do this. All right. All right. Cute little child and a stick. Okay? If you take the stick and you bash the cute little child with it, and the child cries, whose fault is it? The child's fault or the stick's fault? It's a question. It's that's right. It's always the child's fault. Okay, it's always shut up and take it. You know, and I did this because it's right. We have hardware. We have this little box we assembled as our child, and we have this big mean old stick that's our automotive system with noise and everything, and it's bashing this thing to bits. And every once in a while it cries. Okay, now first reaction is shut up, baby, take it. But then after a while, you might say, well, you know what? Maybe I should put some protection around it, or I should get rid of the stick, and maybe it won't cry anymore. It's kind of a graphic example, but it's a different way of thinking about it. The automotive systems are horrendous for noise. These things, I don't even know how these things are running, quite frankly. I mean, I've seen boards where I can't believe they're working, but they do. Now, a lot of them don't, and they blow up or do whatever. We just want to see what you can do to help it a little bit along. Okay? All right. I'm going to go real fast with this because either that will be here all night. So there's noise. Everybody knows what noise is. Noise spikes. There's things sparking. There's fumes. There's gas. There's temperatures. There's vibration. There's stuff spewing everywhere. There's electrical noise. And the box can shrug off some of it. Some of it brings it to its knees. And if you take that box and put it on another car that worked fine on car A, it won't work on car B. Now, why? Why does it not work, Bill? Okay, I'm sorry. It doesn't work because it just doesn't work. Everything's different. Every install is different. It's magic. Okay, you're playing with magic here. I hate to say it, but a lot of it is. And a lot of people say, well, I did this to make it work. Why did it happen? And I'm like, I don't know. Yeah, it did. Do it again. But it won't work the second time you do it. See? And that's what's fun about this. Okay. Sources of electrical noise, you have radiated noise, sparking things, ignition, electric motors, starter, wiper, heater, spew out noise. You have other noise that's current-induced, charging. Electric motors can change current inside of wires. Noise can occur when you're starting. And we're going to talk about that. We're really going to go over this because this is a way you can actually check out your vehicle electrical system with a voltmeter while cranking. You can test a lot of your noise out on your car while you're running. And also when you're turning on headlights, wipers, and the heaters, that punk, it's called load dump, will bring this thing to the knees sometimes. But there's ways around it to help it. Yeah, your horn. I didn't put the horn. Yeah. Blow the horn and watch your car reboot. Yeah. All right, radiated noise. Now this is, we all know what this is, and we all have seen this. This is the little low impedance injector, and this little PWM that's putting the current, turning it on and off real fast, the current limit what's inside of here, and then at the very end, when you let the thing go, you get a high voltage spike to make the injector close really fast. Okay, this spews out noise. All right, another thing that spews out noise, this thing, and it spews out 30 kilovolts signals that can spew out with bad spark plug wires, and you got a primary thing at charging at 5 amps at 300 volts kickback. These things shouldn't even work. I'm surprised that any of these things work. Honestly, it's horrific noise generates. Ignition wires, the little red thing, spew noise all over the place. You go out at night and you start your car up, Go tonight, start your car up and look at ignition wires. They're glowing with a corona all over them. A lot of times, good wires aren't. But if you ran your wires for like 3 minutes, they'll start glowing with this corona discharge. And they will tell you, the old times will tell you, when you had distributor caps, look at the glow, look at the little sparks going around there. You know, people will take wires and they get the little metal clamps that clamp it to the valve cover with no insulators, and they're crimping it down in the show car, and you start it up, and now you've got a nice spark after a while going right to ground. You know, you won't see it, so. Okay. One way of detecting noise, and people are doing this on the list, it's working well. Get a cheapy little transistor radio and turn it on and wipe it around your car, and you can actually detect running radiated emissions, things like spark plug wires or wires for a horn while you're running a horn. If it's radiating noise, this will buzz. This will actually go off. You know, just pick a frequency where there isn't a radio station on. So it's just on. Turn up the volume on it and wipe it around. I mean, if you took a radio and you wiped it around this laptop, it'll go bonkers because this thing's spewing out noise. Over here, take it to your car and it'll probably blow up. So, questions? Everybody understand? This is real simple. But people don't do it because they don't think about it. But you do this and wipe it over your car, you might find where your noise source is before you do an install. All right, high current sources, right? Hundreds of amps. This thing can pump it back to here. This thing cranks this over. And what's common about with all this stuff? I have it blown apart, but there's something that's common is grounds. I have to have really high return wires to all these things. If I don't, and it's vehicle grounding, we all have experienced what happens. Yeah. And it's the baby. The baby doesn't react well, and it cries. And, well, there's something wrong with the baby. Again, if you flesh out your electrical system, the baby may not cry. Really think of it in those terms. You can save yourself a lot of hassles and think of it as this thing's crying for help. It's cry, you know. You have to nurture it. You know, sometimes you have to slap it too. Okay. Resistance in wirings can cause voltage drops. Does everybody understand why? We're going to go over this in a minute. Have you heard of this? There's a reason why these are big hunking wires and this is ground. This symbol means that this is connected over here. It's your chassis ground, it's your vehicle ground. Like you said, you got to have straps between them. Very important because what happens is when you turn these things on, you get voltages across here. You actually get voltage drops due to current. We're going to see why in a minute. Okay. Voltage drop in anything, be it a wire, a starter, an injector, ignition coil, anything you're pumping current across, it's current times resistance of the thing you're pumping it across. Okay, it's an equation. Oh my God, an equation! No. Okay. The amount of current, if you increase the current and this stays fixed, your voltage drop increases. This is the most important thing you can remember in all this wiring is that if I have wiring with resistance in it, even a little bit, half an ohm, a tenth of an ohm, if I pump more current and I multiply it by that resistance, the wire itself will throw away voltage. It's gone. If I put the voltage here, I can actually take a voltmeter and measure across that wire. It'll show me a voltage. And the more current I pump across, the more the voltage drop increases because it's got resistance in it. Okay? It's called IR drop. I is the symbol for current. R is resistance. Very powerful to use this because high current sources, a starter, charging system. I got the horn in this one. Heater wipers, headlights. You can turn on. You ever turn on the headlights and you see things inside dim, or you see your air conditioner clutch engage and your headlights boom, or you rev your car up and your headlights flare. Everybody's seen that on the road. They're driving, the headlights dim down at idle, they flare. A lot of these things can be done from voltage drops in wiring or bad grounds that are causing voltage drops. You can use a voltmeter to determine this. We're going to see how in a minute. The other rule you get to learn, you have to remember the other one. Okay, and you all remembered it, right? All right, here's the other one. If you remember these two, you can fix any install. The total voltage around the whole loop of wire is equal to the sum of all the voltage drops. Okay, if I have a 12-volt battery and I have a wire going to a starter to ground and back, that 12 volts that I'm supplying to it, all these little things, the sum of all the voltage drops around it equals what I'm supplying to it. It's conservation of energy. You can't now create energy. These aren't energy creation devices. You use this rule to look for voltage drops. Voltage drops in wiring, they're bad. Okay, grounds, they're bad. You want your voltage to go to your starter motor, right? You want them to go to your headlights, not half of it be thrown away in your wiring. Okay? This is how you do it. Get a voltmeter. Anyone, put it on volt. Step number 1, take your battery, measure the voltage across it while cranking. And the reason why you do it while cranking is because the battery itself has internal resistance, and when you're pumping 600 amps to a starter, or whatever the number is, the battery itself, the little connectors inside and inside of it actually has a resistance, and instead of being 12 volts, it might lower down to 9 volts. That's okay. Just get what that number is and say, hey, that's 9 volts across your arm while I'm cranking. Okay? Move the wire that was going here on the voltmeter over to here. So you're measuring the voltage drop across this wire. You'll be surprised. You might see 1 or 2 volts across it. That 1 or 2 volts is not getting to the starter. It's being thrown away in that wire. How would I lower that number, that 1 or 2 volts? What would I do? Better connectors, wires. Okay? Now, you can crank the starter again and measure the voltage drop across the starter. You want all of it across here as much as possible. This is the thing you want to jump all your energy into, not dumping it into the voltage drop on the wires. Okay, so back a slide, when I said measure the voltage across here, originally I said, let's say this is 9 volts. And let's say I had a volt across here. Okay, this source is 9. I've just thrown away 1 volt. I have 8 more volts left. Hopefully they all go to the starter. So I measure across here. Let's say it's 6 volts. Yeah, oops, it's going away, so where'd my voltage go? Well, yeah, now I can measure it across and do the same thing. Why this is good is you're pumping a lot of current through there, and you're increasing the voltage drops, measuring those voltage drops. It's all you have to do. And if you take and install and you do this, then you're going to say, oh my God, what a crummy car. Yeah?
On a starter, what would you consider a bogey number that's pretty good on the high wire and then on the ground?
I've seen, you should get less than a volt. You should see less. As small as possible. Again, it all throws away, and you can compute your resistance in there. The most critical one is this one here, because if you have a voltage drop across here, it's just like what Glenn said. You've got a voltage drop. Think of it. A huge hunk of metal. This starter's bolted this huge piece of metal that's bolted to a frame, and I got a little wire going back to this battery, back to my source. There should be no voltage drops. And there's voltage drops everywhere. To the chassis. You will be surprised. You could take it from the starter and hold it to the chassis. Or hold it back to the battery. Or hold it back and see the voltage drops. But you have to do it while you're cranking, because you're getting that huge current through there and you're looking at the voltage drops, and it has to be where the path's going back to. Okay. One thing is, if the battery negative is hooked to the engine block, and the starter is, of course, bolted to the engine block, and you're cranking it, I'm not going to get a voltage drop back to the chassis because current's not flowing through it. You have to think of the circle, completing the circle. And the circle means if my battery return goes to my engine block or to my frame, you have to envision in your head, oh, the little electrons are flowing from the starter case out back to this battery. What path is it going to take? And you may not get it back to your metal of your chassis because maybe your return doesn't go that way. You have to follow your returns. Okay? So you might do this and say, oh, I have no voltage drop. Great, but you may not be measuring the right path.
We're just talking about your steady state. No crazy stuff. It's I times R, okay? But when you have lots of noise and transients, it's not I times R. It's I times the reactance of it. And so it's an inductor. The wire becomes an inductor at high frequency. It actually can have more resistance than the steady state R of the wire itself. And that's what bites you in the butt when you install a MegaSquirt. Because you say, gee, let's say that draw a half an amp or quarter amp or whatever it is on the ground. I can run one number 22 gauge wire. But in reality, that piece of wire may have 3 or 4 ohms in it because of the inductance and the frequency of the transients. And that's why you want a whole bunch of wires, because there you've got these resistors in parallel, this inductance in parallel, and it drops, by 2 bits about half, 1/3, collector range, is what it says. One number 10 doesn't get it. It's a bunch of...
In parallel. And it's not so much the resistance where, like you said, they're a little inductor. And we're going to cover that in a minute, but think of, in your brain, think of the little ground straps from MegaSquirt, each one having a resistor and a little coil of wire and inductor, because the wire acts like that. You want, in putting wires in parallel, are paralleling resistors, and that's great for steady state, like you said. But when you now have an injector turning on and off, or they're PWMing, or you have an ignition coil, and that's a return path, you've got this pulse. Now this wire acts as an inductor, and an inductor, all an inductor does, it doesn't like change. It gets mad at change. It tries to resist it. And so what it'll do instantaneously is you'll get a resistance. It'll basically resistance comes out of nowhere just for an instant. But during that time, your voltage now level changes in your MegaSquirt, and you get a reset. Okay, we're going to say that in a minute. But like I said, this is high current stuff. You can use this tech, go home in your car, and then cry afterwards because you're going to see voltage drops. The numbers are you want to get as low as possible. Okay, get it to 0. Good luck. And here's an example. The battery went down to 10 volts while cranking. I got 1.5 volt drop on a wire and 0.5 volt on the ground. I just pulled these numbers up. But the point is, this whole path here should equal this number, or very close to it. I mean, Al swears Ohm's law doesn't work for him. He'll measure a resistance, and it doesn't work. Now, for everybody else in the room, it works, right? It never has worked for you. But it's supposedly a good thing. Yeah.
These resistances are really small on these wires, and they're difficult to measure accurately. Mm-hmm. So that the voltage drop is always going to be the better way to do it.
For these types of things, yeah, because otherwise, like you said, you can't measure 1/10 of an ohm very accurately because your lead, you hold it on the terminal, scrape off the dirt, it may not be represented. So, exactly right. That's why the high current thing flushes these things out, because you're pumping a lot of current. Now, you can't pump, 200 amps through 30 gauge wire, of course, but for this step right here, to flush out your overall charging and your grounds, your engine grounds, there's nothing that beats this for detecting do you have a decent engine ground. Yeah. Yeah, it's Ohm's law. Ohm's law does work. But it does have higher orders, right? Okay.
Don't use analog meters.
Yeah, because analog has a sweep on it, It's good for trending, but you want this here, get a nice digital, and try to get, if you see voltage drops, it could be that you didn't cram the terminal in there good, the way you connect it onto the thing. Just play around with it. You'll get a feel for it, and like I said, you're going to be kind of surprised. Yeah? Yeah, oh yeah. You have a scope and hook it up, man. Do it while you're intoxicated, because if you're sober and you see it, you're going to know why my car even runs. Noise. Take your scope, you're right. Hook it to your 12 volts. Turn on the horn, turn on the battery. You will say, hey, how does this box survive anything? Honestly, it is horrible. This is amazing. These things don't blow up all the time. Now remember, it's not just MegaSquirt. Any aftermarket stereo or amplifier or anything, they all live these same problems. It's not just MegaSquirt. And aftermarket ECUs do too. OEMs do too. They also fail as well for these reasons. Some cases, you don't know where the noise is coming from. Okay? You can't ever locate it. It's there. Just to play with you, to taunt you. And it'll taunt you. All right? The V3 MegaSquirt has some built-in noise protection. Some. Again, it's a trade-off on me having to put 50,000 components in there so this thing will take a lightning strike, or being a little bit on the lean side and letting the end user have to flush out a little bit of noise sources. Because you can overprotect these things too, which will hose you over later on for another thing. Okay, so we're trying to enable people with the knowledge to flesh these things out and to say, hey, you know what? I'm having noise, but there are a few things I can do to try to work around it. Everybody here is done. Every MegaSquirt I hear have wires coming out of it, things are relocated, and they work. And so that's cool. That's what makes this neat, because you can actually get the guts of it and fix stuff.
So don't tie wrap your signal wires to an ignition wire. Try to separate all that stuff apart.
But people do it, right? And this is what happens with me. I'll do an install. It's all pretty. And then I'll start changing things. And, here's a wire and there's a bundle, and I'll lay it on an ignition coil, and all of a sudden things start degrading, and eventually I find, I caused my own problem. So because I'm not super neat. And there's other people, their installs are so neat. Like Alice, his wires were so labeled neat and nice, and you can get noise problems. So, again, stick or the baby. We're going to go over this, some different things you can do for sensor grounds, multiple ground wires, what Bill said. There's TAC inputs. Andy will tell you the torture of TAC. Everybody here, if you haven't had a torture of TAC, you've got some guardian angel, because everybody else here has had TAC problems. They are there. They are just the worst, just to taunt you. All right. First thing, and this is not so clear in the wiring diagram in the MegaSquirt manual, and it may not be in every wiring harness you get. You may want to look at them. But it is good to run a separate sensor ground return back to the MegaSquirt on one of the... MegaSquirt has multiple ground wires. You might say, well, how come there's 9 or 10 pins dedicated to ground? You've chewed up half your pins. Well, there's a reason for it. One thing that Bill talked about, having multiple parallel wires is better than one big fat one. And it allows you to do separate ground return paths in, for instance, like the sensor. Sensors, what if I had here the starter motor? Okay. Well, you would have a horrendous voltage drop there, right? Well, what if I'm passing in the injector ground through here? What if I'm running an injector and the injector ground is going through the sound thing and it's going through here? And I'm pumping 5 amps through there. And this is a 30 gauge wire, 20 gauge, whatever. You're going to get a voltage drop. The voltage drop is going to translate into a voltage drop from here to here. If this has a certain voltage potential, it's going to be different here. And what do you get? You'll start seeing, like Andy says, the dance. You start seeing the bounce, the sensor bounce. You'll look on Megatune and you'll see all the analog things, junk, 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 junk. They'll dance. If they're dancing, there's a problem in your grounds. You don't have to rip your board apart to shreds and say it's dancing because there is some high current path going through here and it's causing a voltage drop, and you're seeing it in A to D. It's that simple. And I think people here understand that, but there's a lot of people who don't understand it, and they see the sensor bounce. Like Andy says, you crank it over and you see sensor bounce, stop. It's like exactly what he said. Any questions on that? Pretty simple, okay? Bill just talked about this. Run multiple engine grounds back to the MegaSquirt. Now, I personally like to ground it back to the engine block and make sure that there's a battery sitting out here with a big wire going back to it. And I fleshed out to make sure that I don't have a voltage drop from my engine block to my battery negative terminal. But you can because they degrade. I like to go back to the engine block because so many other things come back to a central clearinghouse for grounds. I mean, Bill can talk about how you want everything to come back to the same point. Now, it could all come back to your battery as a return path. The problem with that is if you have your negative battery terminal starts to corrode or your terminals start getting dirty, you're going to now start introducing this ground bounce. Because if it's going back to your battery from here, then if you start getting a resistance in that wire, it's going to start causing you problems. So, my opinion, the best place to put is the engine block. It's the biggest thing. Most things come back to it. Your starter is grounded to it. Your charging circuit, the return of your amp, your alternator dumps to the block. And if your alternator's on and you have that fat negative wire back to the battery and there's a voltage drop there, the battery's going to see a voltage drop. This is why a lot of times your battery doesn't charge up. Wires are bad. Or it won't start. I think it's better to put it back to the engine block. But you can do it what you want. Questions? And everybody understands why? Why do you run more than one wire? Why? Bill can't answer. And what does the inductance do? It's for transients, right? Does everybody know what a transient is? Other than me? Yeah, that's right. These are transients mean anything that's a fast rise time, right? It jumps. That's a transient. And inductors, they hate transients. They will resist transients. So what they do is they resist it by becoming a resistor for a split second. You get a voltage drop during that. Then it comes back to it. Then it self-adjusts. All right, questions? We're almost through this. All right, I wanted to show in the V3 some of the hidden layers that you never get to see because they're hidden. Only lucky you get to see them. And of course, they're not rendering very good on the screen. what's the point here? But to kind of show you, on the V3 board, it's a 4-layer board. 2 of the layers you can't see. They're hidden from you. What's in them, though, is there's this big area here. It's called a ground plane. It's a digital ground plane. It's also shared with the analog. It's not 100% the best thing we could have done, but for a 4-layer board in the layout we have, it is the best thing we could do. If we had a 6-layer board, we could have broke out the analog to a separate ground plane. And I think with MS3 we're talking that. It just makes things better. But this is adequate. People can run this adequately. There's no problems with it. So this is the ground plane for the digital. This green is another ground plane. Now that's for the high current stuff. All the stuff on this little heatsink bar are your injector drivers, your flyback path returns. When your injector closes, you get that 70 volt spike, gets dumped by the transistors up there. This whole green comes back to the connector in one point here on the top layer, and over here in the ground plane, it also comes back to the connector. They only come back to one place through the connector. That's for a reason. It's against trying to ground back things to one place. If I had had this green thing here with all this high current stuff, and I had hooked the ground there, and onto this other ground plane, I hooked it together there, and I had all this wire coming out of here, what would happen? Yeah, so this high current chunk would go leaking through all this stuff with all this nice processors and everything here. And you can start, if there's any voltage drop in the ground plane, without trying to pump 6 amps there, maybe a little bit, you'll start seeing ripples on the ground plane. That's why this ground comes back through here. This ground is separate, but it comes back to the same point. Okay? And that is important because back here, when we showed this here, though that whole strip is a bunch of grounds, you can pick the high current stuff to come back. Let's say you pick these 4 wires coming out of this section. You can choose what you want back for your high currents. And then down here, I'm picking another part to here. The sensor stuff is going to go into the digital ground plane, go through the processor, and loop back, through the VREF. The main stuff is going to go. You have your loads here. These things are turning them on as switches, but that green area is going to come back and then out here. So you basically have you have a high current path and a low current path. Okay? And to show you, this is the high current path here. And this is that whole green area where the heatsink bar was. You don't see it over here, but this is the edge of it. This is the connector output. And all these little things here have little X. You can't see them. But trust me, if you ran up here and looked at it, all the way across here, there are connections. You might be able to see it here. They connect off here. And the reason why they're little like that is that they're called thermal release. When you're getting the board made, if this was a solid to this ground plane, when you're soldering the thing up, you would have to heat the whole board up really before the solder would adhere to it. So these are called thermal release. That's the CAD program does that for you. Anyway, all the way across, they all come across all the pins. And this is one layer. And then on another layer, the ground plane, same thing. They all kind of come here. This is a 12-volt return, which we're going to talk about in a minute. But these right here all connect to the ground plane. So what you're having is 2 layers. The DB37's touching both of them. They're connected. That's what's going through them. The DB37 pins are going through, connecting those 2 layers. But I can pick this down here, if I wanted to be my sensor return, and the sensor return is going to have its current loop go to this ground plane, and then I can have the other high current stuff hooking out. Let's say the wires down over here, and it'll loop through here, go out here, and go out through the wires. So it's common point, but you can separate them. Okay. Again, if your wiring harness shares the sensor leads with high power anywhere, you're going to get bounce. You may not see it all the time. It's there. Don't do it. Questions? And it's kind of technical, but I think people are understanding, right? There's a difference. Thinking ahead loops. We'll post the slides so everybody can see how this works. Okay. What would happen? Well, nothing unless I had, but it's also, this return path can go through these wires, and it should, but there's also one return path that goes here, back in here. Right? It's a separate way to it. It's another one of these parallel wires. So you can get a little bit of current on here. And if you didn't put enough on here, Well, it's going to share the load with that, like it's parallel inductors. You don't want to do that. If you see the picture I have here, the sensor ground goes back here, and this is a ground loop. This could be a potential ground loop if I hooked a wire here to here, because I'm wanting this ground to go through here, up to that ground plane, and around here. That's what I want. I want that. If I hooked a wire from here to here, some of the juice will go to the engine block back here and back in here, and it can interfere because I'm getting a voltage across here. Tunk, tunk, tunk. It's moving this a little bit. That's a ground loop, and by keeping them separate, you kill the ground loop.
Is there such thing as a single wire temperature sensor? Are they always two wire?
No. Well, sure. For your gas gauges, the older ones for your gas gauges is a single wire, and they ground through the block.
Right.
Yeah. Right. But you don't use them for instrumentation precisely because you can get.
That's a good, yeah, see? Now, clean. See, people understand it.
Which was to note on the directions that use the ground exactly with the squirt, don't use the ground with the block. Because I made a mistake once of needing ground, so I just went down to the block.
Right.
I started it, I watched the temperature.
Right.
And I yelled at me, and I said, I don't get this.
Well, that's why we're doing this here. So now it's laid out here, and people now understand that, oh, that's why. There's a reason for it, not just, we'll just hook it up here because I say so and I know what I'm doing. There's a real electrical... That's it, and it's got a lot of damping. Who the hell cares, right? It's not going to do this unless it's an auto meter.
The OEMs do this sort of thing precisely because of the ground noise.
Yeah, they wouldn't put an extra pin on here. An extra pin times a million cars.
One pin rather than two.
Look at your mid-60s and earlier model. 3.7, I got my quote, it's a single wire for the temperature.
Right.
For the gauge. So.
Okay.
How my dart's set up too.
Good question. Bill's got something too. Listen to the God. Bill's ground God.
But make sure that braided wire goes through your engine block and your chassis to the control. If there's a couple of other things that you attach, so that won't lose you particularly if you think you should go back to the battery and use it for a
Yeah. That was a good question. That was a very good, with having the two, there's a reason why there's another thing, and use them that way. If you run an external map sensor, also use the sensor, use it with the map sensor, because if you high it back here, it's a signal. It's anything is a signal, and we're going to find in a minute, I screwed up on a V3 board in a couple grounding points, and we're going to show you how to fix them. This is where you've all experienced them and said, well, if I, sacrifice a chicken next to my MegaSquirt, it works. Well, you don't have to do that anymore. You actually can figure out why. This stuff's not magic. It's just a little bit of knowledge. Yeah, well, no, I'm going to go through the flyback, and you fix that. All right. This is one that kills everybody with low impedance. We just had someone here. Whoa, if I hook low impedance things, it all goes bonkers. That was partially my screw up, partially because I painted myself in a corner, connector-wise. And so I try to take the easy way out, and for some reason it'll work, with some people it won't. When you're using the low impedance injector driver, and you're using the PWM, some people will notice you get processor resets, some screwy results, sensors will bounce, bad things happen, it's just noisy, can't get a tact signal. It turns out that the 12 volts going into the MegaSquirt, it's a small wire, it's a single thing coming in, because originally with the MegaSquirt, it just had the 12 volts coming in for all the stuff. What we discovered a long time after we designed it was when you're doing PWM, you want to be able to take the flyback voltage. Okay, this is how it works. When you take an inductor and you charge it up, you put current through it. Okay, at first we talked about earlier, inductors don't like change. They're screwy. So you put current into them, they resist current flow. They don't like to flow current, and then after a while, they get used to it. It's... Okay, I'll let it flow, and it starts ramping up the current. Now, if you take the current away, it gets mad again, because you can't keep them happy. So what it tries to do is it tries to produce a current to counteract what you took away from it, because it doesn't want to change. And what that results in is a voltage spike. And that's called the flyback. Ignition coils exist on that rule. Ignition coil primary, you charge it up, and you take away the juice, and the primary coil flies back like 350 volts. that 350 volts gets magnified by the turns ratio in the transformer to 20,000 volts. That flyback is critical. If you don't have that 350 volt flyback, you don't get the multiplication to your secondary to make the spark. That's all it's doing. Injectors also have a kickback. Now, that's great. And I can PWM them, and I keep getting these kickbacks. And there's a circuit, it's a power zener that damps that away. Well, what happens is, if you PWM it, that zener is constantly on, and it's dumping heat, because to get rid of the flyback, it converts it as heat. So if you do this, the zeners blew up. V2.2 boards, they blew up. Okay, the PET drivers blew up, and because the flyback blew up. So we put another transistor in there that's a PNP transistor that just gets turned on during the PWM phase to recirculate that flyback pulse back through the 12-volt battery return going into the MegaSquirt. Great. You have an injector out there. It's got 12 volts on one end. The other end goes back to the MegaSquirt that's grounding it. But on the PWM, the flyback voltage is going through the positive 12 back out. And, people are laughing at me. Here we go. Picture's better than me talking. This is how you hook up an injector. You hook it up here, and this goes big, heavy current, and this actually goes to some of these transistors in here. There's also a 12-volt line that powers the MegaSquirt. Notice it's littler, and it's only a pin, but it's a little wire. This has a relay in there, the ECU relay we talk about, and then this goes off some godly place into your wiring harness. I got 12 volts out of here. Pull the wire, it's like doing a bypass. And plug it in there. There's my 12-volt switch. Great. It goes off into the dash. Well, all the wires. Off to God knows where. Okay. I don't know what gauge they are. Maybe 10 gauge and maybe 50 gauge. Who knows, right? It's off in the dash, going God knows where, through connectors and everything else. Through the ignition switch. And what happens when you have resistance in that wire, anything in there? You get a voltage drop. All right? When I first turn on the injector, what happens is juice comes from here, through the injector, through this little thing, through one of these transistors, whichever one it is, out to ground. There's your path. Okay, that's when you first turn it on. The PWM, what it does, though, is it takes away the juice, puts it on really, really, really fast. During the PWM phase, the juice comes from here, through the injector, up here, to a flyback transistor, flyback damping, out through that little 12-volt tiny wire that then goes off to your ignition switch and everywhere else into your system, back to the battery. That's the return path. And what happens if we had resistance here? This point will bounce around. This 12 volts also goes to the voltage regulator that then steps it down to 5 volts that regulates this whole thing. And if you start bouncing around with this goes out of regulation, you get a reset here. Okay? Not good. It wasn't optimal when I did it. My fault. I will say that. I will also say, though, again, baby in the stick, this wire goes off to Never Never Land, and God knows what type of resistance levels I'm having here. So we're both the fault, but, there's a way to fix it. Bill actually fixed it on the Spectre board. He actually fixed it for this reason. A lot of you all know this trick, so. This wire here is the 12-volt source. There's 12 volts coming in here, into this connector. This little wire here goes off, and it goes all the way over here to the voltage regulator. This return path here, this is the transistor during that flyback pulse, when I'm taking that energy that's stored up in the injector, and I'm turning it off, and I got to dump it back in. That's dumping this through, it actually dumps, this is your injector driver, it dumps it this way back out to 12. That's great, but if you have a resistance here, this point will bounce around. If it bounces around, this guy gets mad. So the solution is, well, give it another path out, right? Chop it here, take this and run a wire somewhere out of it, and put this back at the 12-volt source where the injector is. Because remember, during the flyback, the injector is acting like a little generator. He's generating voltage. You want to loop back to him or her. What do you call your injectors? I don't know what gender they are. People have done this. This here's a lot of noise. I think people here have done it. Who's done this? Everybody? Yeah, the whole back of the room is cheering. We're going to fix the board so you don't have to do this. God knows what connector pin we're going to use because we have a plethora of leftover pins, right? Another solution, take it at the source. you can put a capacitor and a resistor. I don't have a resistor here, but it's called a snubbing circuit. During fast transients, what you're doing is during that really fast brief second, instead of pumping all the way back through here and bouncing to 12 volts, you're shunting it with a capacitor resistor across the injector. Now, what values to use? I don't know. I mean, you can put it into SPICE and figure out your inductance and figure out the frequency, figure out the transients, or you can use like 0.1 UF and maybe a 100 ohm resistor here. It may have to be a half ohm. Huh? Or remember, it's 2 banks. So you can take it back to the bank, right? Or back across each ejector. You can actually put this right at the source. I would do it at the injector, because then you're taking the little current loop and keeping it local here. It's a pain. It's not the best way of doing this. But if someone's running a throttle body with 2 injectors, they can hook that snubber up there, and it won't hurt it. And actually, during flyback, it also will help as well. Yeah. Good. Well, look, do you see the wires? Okay, I just said it, follow the words. This is out there. I can do it. Your synaptics. You don't want to put it in series with the thing. You want to put it, again, this is the little generator during the flyback. You want the little ball bearing juice current to go through here, because capacitors like change. They like it when things go bad, because they'll let things flow through it instantaneously. And then they say, stop it, I won't flow anymore. And then a resistor kind of is there to limit the current, to tweak it up to have a nice response curve. It's called a snubber. And there are a lot of ECUs out there who do this as their flyback taming mechanism. You can do it too. I would recommend taking the 12 volts and pulling it out. It's an easier mod. This works as well, or a combination. Well, if you do a diode, you're doing exactly what that thing does. Because that's really what that PNP transistor is. They're really acting as a diode back to 12 volts, but it's a switch diode. It's only on during the PWM phase. When you're trying to shut the injector off finally, that thing goes away. It's effectively, that diode disappears, and then the injector has a big flyback pulse that gets dumped to another PNP, which is acting like a Zener diode, because you want the injector to close quickly. If you put a diode across an injector, we did it on the V1.01 boards. People found out that their close time with their injectors slowed down. You would tell it to close, but they actually would close a millisecond later, because because of the diode drop across there, you get a long bleed down of current. Remember, the injector is current. It's generating voltage and current while it's being turned off, because it doesn't like changes. This thing was slow to shut. It would just shut. The trick of that is, that's why there's a flyback. What you're doing is, instead of putting a diode across here, you're putting basically a voltage drop across here. With the flyback, you're putting like 30 volts across here before it starts conducting. And by putting that voltage drop across there, you're basically dissipating energy. It's a voltage drop, you go through it, it's actually throwing away energy, and it makes this close quicker. That's why there's all these little tricks up there, all these parts. One are getting switched in while you're PWMing, then at the final one, it goes away, and then you get the other one kicking in to do your flyback pulse. You understand? Okay.
And that's the other half of the reason 100 ohm resistor is there, because you don't want that capacitor to act like a short when you're trying to close the injector, because that'll slow the injector down from closing, just like the diode would. Only worse.
And why not use high Z injector?
Why not?
You can use high Z and go power goes away.
Yeah, high Z, you don't have this problem. This is all low Z.
Is there an advantage to using a low Z injector?
What you find, supposedly, you can get bigger flow rates with low Z. They're throttle body ones, and they were throttle bodies bang, 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 bang really fast. So they had to open and close really fast. So everything you did was to make those things open fast, because they were every pulse, every tack pulse, ignition coil, they're firing or they're alternating. If it's port injection, the duty cycle is much lower. But they were designed when they were in a throttle body, so they had to pump a lot of fuel. Every time it squirted, it had to fuel a cylinder up. They tended to be bigger. Down here in the port, it only has to fill enough for one cylinder, not all the rest of them, because they got their own injectors. Yeah, resistor pack. These are all different ones. But if you can there's no advantage to low impedance injectors if you can find a high impedance one that does the work too. Yeah.
I was just going to say, I think that'll help reduce noising with high Z injectors.
I'm sorry, what?
I think it'll help reduce the noise.
Absolutely, you're absolutely right. It's better all the way around. Yeah. You're absolutely right. Absolutely. All these trickeries and all these little games and currents, all that go away. You know. Here's another trick. These stereo capacitors are lovely. They're actually putting these in OEM cars now. 1 farad, 2 farad, 3 farad. You can buy them at Best Buy for $30. You put one of these on here on the 12 volts. Instead of there being a ripple, this is your reservoir now. Now be sure to put this. Make sure there's a switch here, which may have a voltage drop across it. Put it here so that the current can actually go back to this capacitor. People on the list, I know on the MegaSquirt, we're pushing this a lot because it's a smaller board and it's a little more susceptible to noise. We're pushing it there, and one guy restarted, wow, I hooked the capacitor up, and the car starts it spins over so much faster. What does that mean? That means it's got a voltage drop somewhere, right? But he was happy. Oh, I put the capacitor on it, the starter spins over faster. You want to say, well, great, I'm glad you fixed your problem. You want to also say, you got a voltage drop somewhere. You don't know where it is. The introduction capacitor shouldn't change your starter speed. If it is, you're correcting for something. But those are the things you look for when you get a result and you see something else. You're going to bring, well, now I have something else going on, and maybe I didn't solve the problem, but it helped it, right? So, I love these. These are cool. Now, here's the problem with them. As soon as you hook them, if they're dead flat, you hook them to a battery, you'll get a surge current. Like, they only have circuits out there. And I have a circuit. If people want to build this, a couple transistors. What it'll do is, if this sucker's dead, no voltage, there's no charge on it, you hook it up to a battery. What you should do is hook a resistor in here. Maybe, a 1 ohm, 100 ohm, maybe a watt, 2 watt resistor, and monitor the voltage across here until it ramps up to 12. Then take the resistor out, and it can be across the battery forever. Because it'll follow the battery and do this. But it's that initial, this thing's dead, and I'm hooking up the battery. Capacitors, again, when you first apply current to it, they're like, bring it on. And they'll suck current in there, and they can overheat because of the surge current. These things actually can grenade on you. It's cool. So, I have a circuit, though. What it does is it switches a resistor in while it's charged, but it monitors the voltage across here, and when it gets almost to the battery voltage, then it just does a hard connection. It bypasses it, yeah. So it's stereo. You can buy them from stereo thing. This is one of these things with the stereo audio. Why do they have a capacitor? Well, they got a 300 watt, 1,000 watt power supply, and they got to make a speaker go boom, and so it's got to take the surge current and just dump it into the speaker cone. And they ain't getting from all their voltage drops in their battery and your headlights flare and everything else. Again, it's the same voltage drop issue that you all have discovered. So, the charger, yeah, you can buy them. Yeah, the battery tender thing or capacitor tender, whatever you want to call it. Yeah, I mean, one of the things we're thinking about in the relay is maybe putting this as part of a relay board, an improved relay board, where you can hook one of these suckers in there and maybe have that circuit in there. So you can you can have a nice central place if you wanted to wire in a capacitor, just because it's a neat thing to have. With, switching right. So if there's interest, we can put it on there. Yeah. There should be a switch here. Yeah, there got to be a switch here, because otherwise this thing will be juiced forever. Sure, I can do it. Yeah, my PowerPoint skills are phenomenal. Yeah, you know how many hours it took me to draw this? I'm there, dude. Gee. No, you're right, because someone will hook because if you hook this, and what'll happen? You'll never shut your car off, right? Everybody knows why, and they laugh, but my car won't shut, and they'll email Al, because I won't take that. And they'll give it to Al, and Al will go through the code to see why it won't shut off. Right? And what did you do? You went through the code, right? All right. This is the other thing, the fast idle. Oh, everybody loves this. Fast idle circuit is garbage on the D3, right? It was, again, to my defense, it was originally designed to turn a thing on and off. But people said, well, these other valves out there, let's PWM it. And that's a great thing. I'm glad they did it, because now it's opened up idle control where you couldn't have it before. it tortures the V3 board. I just saw a board floating around here where someone did idle speed, the idle valve change, and I'm glad you do it. If you're going to run this thing with a PWM, don't use the thing. The extra site has a nice circuit to do it. You can also do some of the stuff here. Here's the reason why. This is a circuit. We all can read circuits, I know. Anyway, this is the switching transistor. It turns on that your fast idle valve has 12 volts here. Your fast idle valve, if you think of it being there, juice goes through here, goes to this transistor, through this resistor, down to the ground. That ground, what ground should that go to? Yeah, it doesn't. Why? Because, yeah, it should. Okay, yeah, okay. That's right. Otherwise, I wouldn't have listed it up here, right? You're right. It's right. I mean, and it didn't. And actually, when you shut the thing off and you get the blink, this should go to the high power ground too. Now, I didn't catch it. When Bill took the V3 board and made it to the 357 surface mount board, we switched out the drivers to a 3-amp driver. Bill calls me and says, Bruce, I don't know. Bill will tell you, he'll say, I don't know what happened here, but I don't know. Maybe those grounds should not go to the ground plane. And of course, I'm like, yeah, I had no excuse. Yeah, you're right. I messed it up, But he did it right on the 357 board. That's why the 357 board, surface mount board, you can drive these and you don't have to mess around with them. V3 board, you have to muck around with it. There's so many different mods. This is what I would do, or I do what the extra guys do. They use a better transistor here, okay? And you should do that, because this transistor, you should be switching an amp through it in PWM. It just goes. But if you wanted to, you can try it. What I do is I lift the leads up here, and I hook them to this. This is the ground, the high current ground. We saw it earlier, right? Just hooking it back over here where it should have been. All right, that's one method of doing it. There's other ones where you just you rip this transistor out, and oh, by the way, how many people have cursed my name because these 3 circle leads that go through there are so close? Who's cursed my name? Raise your hands. Good. Yes. Oh, the meter reactor's like. Yeah.
Oh, Bruce, I'm wrong. I make a lot of money with that.
Okay, you don't want me to fix it then. I will leave it.
I love you. It's going to change.
Actually, it won't get changed. It was OrCAD layout had a footprint, and why should I change what OrCAD gives you? And it's horrifically bad. Everybody emails me, I love your design, but those transistors, they short out. They're a real pain. Yeah.
The question I have about that, wouldn't that create a ground loop back to the 5-volt ground plane?
No. You loop. Oh, I'm sorry. You lift these leads up. No. You don't just hook a parallel wire. I think I said it earlier, but I probably take that, stick it up in the air, like it's dead. Then hook a wire to it and run it back. Yeah. If you just hook a wire here, very good ground loop. You're thinking loops. Yes, absolutely. Good.
Replacing the little transistor with a tip 120 type. What not many people realize is if you're sticking it into the R37 spot, is that you bend that pin down and pick up the high power ground right there. Then you only have to run 2 wires back to the
Q4 spot.
To the Q20 or.
Okay. Cool.
Q4 rather.
Yeah. There are so many different ways. This is what's so neat about the board. These flaws gets to be your games. You get to then, right? Otherwise, you'd have nothing to do and say, I just assemble it and it worked. That's all right. They're featured. This is a feature set. Okay. Now, VR circuit. Ooh, everybody's had a silly VR circuit. And it is the one, VR doesn't work. Al emails me, another one who doesn't have the VR working, like with the ... like laughing. Now it's you get to work on this problem. It's not my deal, right? Yeah. All right. There are at least hundreds of different VR sensors out there, and they all have different outputs. Why? Because engineers, they can't just use a standard thing. They have to tweak it. Otherwise, it's like programmers. They can't reuse code. They have to change code. Now, I'm not saying anything here. It's just in general. People reuse stuff, right? I mean, I do it too. I can write that loop better, and I change. We all do it. We all have this, I think, for whatever reason, we do it. Well, VR sensors, every day it's a new VR sensor, right? Electrical engineer is the worst, the software guy. If he's a software guy, you can roll it back. You roll in a new VR, it's there, and it's a new part number, right? It's just the worst problem. The V3 circuit has some adjustability in it. But you can't fix them all. And this is a situation where one circuit might work with a class of sensors, another circuit might work with another class of sensors, one circuit might work with all of them, but not with others, and it doesn't mean circuit A is bad or circuit B is better. It's like that. It's just, it works with some, doesn't work with some. So what you want to do is figure out why it's not working, what can I do with what I have to make it work. Okay, that's the goal. Try to figure out what the problem is, work around it, because we've worked around ground loops and everything else here. Okay, VR sensors, we all know what they do out. They pump out a voltage, and the voltage gets larger when the RPM goes up. Depends on the number of teeth you're looking at, and you can get 100 volts out of these suckers. Okay, and also when they speed faster, they're little voltage generators. They're like a microphone. They're like this little microphone here generates voltage because I speak. These things generate but much more voltage. They have irregular signals coming out of them because of the different missing teeth. They're just horrific. All right. Hopefully you all can see this. This is the VR circuit down here. This is the opto. And opto's, I think we flushed the opto out. That works pretty good. Everybody knows with wing diodes and ED capacitors and everything else we've done through the years, this is a pretty good circuit. There are things you can do. For the most part, it's a good circuit. VR has had its tweaks too. I'm going to explain real quick how it works. Y'all can go to sleep if you want, but if y'all understand why we're doing this, the VR circuit, the VR signal has a positive and negative amplitude. It's a sine wave, kind of a sine wave. Okay, some sensors out there, the ground return from the VR source is grounded. It's hooked to a ground somewhere on the engine block, some horrible ground out there. Not a nice, clean sensor ground, but it's out there. Not all of them. Most of them have the two wires coming out, and you get the two wires, and they go back to your MegaSquirt. Okay, the circuit we chose only because there are some out there that are grounded, and you want to look to see when that symmetrical signal goes to ground. I need to know that zero crossing point where it hits zero. I chose a circuit. Okay, it's a trick used all the time. This is a transistor. The VR circuit comes in here, goes through a resistor. There's this capacitor here. Now, on the early VR circuits, this was a 0.22, I think, big capacitor. It was done that way because this circuit was originally designed for a distributor pickup, which may on a V8 has 8 little tangs, and it's called if you can. 4-cylinder has 4 of them. It really wasn't designed for a 36 minus 1 tooth wheel or a 50 minus 2 or whatever, A lot more teeth coming in. The bigger capacitor here, what was nice about it is, again, capacitors, when things change, they like to shunt current. And if it changes faster, it'll shunt more current. What happened was, when the VR got a big change of current, a lot of it would get shunted by this capacitor and go back. And so it was a nice voltage reducer, the 0.22 volt thing. Great. It's instead of a lot of the voltage having to go through this, or actually go through this loop back to ground here, it's getting shunted through here. The problem was, it's a big capacitance, and you get something called a phase shift. The signal coming in here and the signal that this transistor sees is shifted in time. And if you're looking for zero crossing and you have an RC circuit, as the frequency increases, that zero crossing point gets shifted out. I forget if it's which direction, if it's leads or lags. Do you remember, Bill? Leads. Okay, it leads. Bill says it leads, so it leads. That changes your timing point at higher RPMs. That's bad, right? Why your zero actually goes at a zero somewhere else where the tooth is. It's in between the tooth. Because that capacitor, the 0.22, actually caused a phase shift. Great. All right. Well, you fix it by reducing it to like a 0.01. So a little bit of the current's still shunting. Anything, it's a high frequency noise thing. But what's happened? Now, more of the juice goes through the transistor as a current path. So the higher thing, now the transistor is conducting more. That's okay. But it's just moving it now, more of the burden's on this transistor. And we're going to see in a minute, I screwed that up. So, not screwed it up. It's where I put the ground. The ground. This is a grounding seminar, right? Okay, here's the trick with the circuit, though. There's the base of the transistor, and here's the emitter. There's always a 0.6 volt drop across this. This voltage here is always 0.6 of a volt higher than that point. Always. Within the voltage supply range. You put 100 volts and you have a 5 volt, it'll rail, but it's always higher. Why do you think I did that? If I have 0 volts here, I have 0.6 volts here. Anybody? Here's the quiz of the day. Why would I do something like that? Huh? No, it's not noise. It's not noise. Op amps. He's got it. This little thing here is an op amp. It's really a comparator, but it's got a little bit of feedback on it. We'll talk about it in a minute. It doesn't want to see 0 as one of its inputs. It wants the input rail a little bit higher. So this 0 volts becomes 0.6 volts here. The op amp can deal with it. And if you notice, an op amp, what it does is it looks at the difference of the two inputs, and the output will snap based off one's higher than the other in voltage potential. Look at this circuit right here. This is the same, basically the same thing as this. It's symmetric. This is the reference. This always here is this 0.6 volts here. Outside of this hysteresis, which actually biases it, kicks it up and down. So when you're actually going one direction, the bias point changes a little bit. And you can adjust the hysteresis so that you have, once you go through a 0 crossing, the set point changes over here. So you have to come back up here and cross it here, and then it changes again. So it gives you a little noise immunity, and you can gronk this resistor, lower the value, and that step change will be greater. And we're going to see them in a minute. That's why I did it. It's 0 crossing. It all comes back because people wanted to have single-ended values. It's single-ended VR sensors. Okay? All right. We're almost done here. This is the last.
Because otherwise, you can't swing below ground because you don't have
right. Because your supply on the supply on this thing is ground. You can't go below ground. This thing has to live between the rails. These inputs have to be between the rails, and it has to operate between the rails, meaning 0 volts and 5 volts. You can't. It won't do anything if it's less than that. In fact, it can make the output go bonkers. This is a simulation. LT Spice. I put the circuit in there. Same circuit. This little thing here is our VR circuit, VR sensor. It's generating. I picked a sine wave. It's not exactly a sine wave. Let's just say it is. And notice here, you can barely see it, but there's a blue output here, right here. That's the output of the op amp. And you can see as this thing goes through 0, this output snaps. It's an inverse in polarity, but it's snapping at the 0 crossing point, all the way across, right? That blue line there is for the output. This green line is what's going in from the VR circuit. All right? No magic. What I'm doing here is showing that whatever the voltage is here, at this point here, it is a little bit higher. It's at 0.7 volts. It's hard to see in this scale here. I think I have a 10 volt scale, or it's a 5 volt. But it's the blue is a little bit higher. It doesn't go below 0, but this is what's being presented here. So it's always a little bit higher because this is at 0.7 or 0.6 volts, and the other input's at 0.6 volts because it goes to that biasing thing is just kind of sitting there. Okay? Just showing you why that transistor's there. It's not there for a reason. Okay? What I did here is look at this op amp, which is really a comparator, looking at this hysteresis knob. Okay? The hysteresis knob, what it does is, like I said, when it goes in one direction, you pass that point where the op amp comparator mode sees it, its reference changes the other way. And you can see the action right here. When it goes down, the little hysteresis comparator and switching point goes up a little bit. And when it comes up the other way, it snaps down. You can see it right there. That's the point where the output will snap. It's just a little bit of hysteresis. And this value is 100K. If I lower the hysteresis value, on our boards, it's cranking it forward. Hysteresis is cranking it clockwise, lowers the resistance. Look at the point here. And notice, when the green goes up, it has to go cross here. This thing goes to this point, and it won't respond until it's gone over here. It's a hysteresis. It's a moving hysteresis. That's what the magical hysteresis thing does. If you put too much hysteresis and your voltage thing doesn't swing enough in here, it'll never detect it. Yeah, so that's why there's knobs and there's trade-offs on this. Okay, we're almost done here. I swear. Okay, when the VR circuit doesn't work, a lot of times the input is swamped. Your sensor puts out a lot of voltage. You can increase the series resistance on the VR positive going in, add more resistance. Sometimes put 5K, whatever, up to 10K, to reduce the signal strength, the loading on it. Also, the capacitor we talked about, how it originally was a big capacitor, and I made it little. You can increase it again, but again, you can have some phase shifts at very high RPMs. This is the biggie right here. I didn't do that on the board, and we're going to see now that y'all are ground loop experts. You're going to see why. Okay, and you invite a hysteresis capacitor. I'll tell you what that is in a minute. Okay, here's the problem. There is no VR minus return. It comes back where? On your where does the VR return path come back into your V3 board? It's a ground, but which ground? It goes back to digital ground. But look, let's say I picked some pin out here. Let's say that it's got to go through all this stuff, and this is 70 volts and current going through it. It's dumping it on that digital ground. Wow, whoopee-doo. I mean, it's really making the digital ground go bonkers at times for high amplitudes. What you can do, instead of having it come back on the ground here, you can run a wire back to C31 because some of the current gets shunted through there. Run a separate wire back to your VR minus, so you bypass all this ground layer and you're putting it back to the thing that's helping you shunt. The capacitor helps you shunt, and so does this point right here on this Q22, the ground on here. So one of those 2 points, have it return back there, and again, it's a loop, right? You want to maintain the loop. And this thing is a voltage generator, and the loop loops back, and instead of the return going all through my ground plane and crumbing up my thing, it's going back to the separate wire back. This helps, and I think Bill actually did it on the Spectre board. He did this. So, again, the Spectre board fixed the problem that I introduced. Okay? Questions on that? This helps a lot. A lot of resets. You're getting a reset. There are 2 types of resets. There's a reset that's ignition trigger reset, and there's a processor reset where your time goes back to 0. This will fix the time processor going back to 0 because of this voltage on this ground plane, it's causing a voltage regulator to go out of regulation, or it's just making the ground plane bump around, and the processor sees it as a reset, and he gets a processor reset. It's in the ground plane. It's a transient in the ground plane. Okay. Another thing you do, and we're almost done here, I swear. There is the op amp here. There is that hysteresis. You can actually put a capacitor across the hysteresis adjustment. What that does is this little, when it does the transition we just saw, it actually makes the set point much further away, but then as the capacitor bleeds down, it approaches this point here. So it actually pushes the threshold out even further. So as you start crossing it, it says, no, now your threshold's way up here, and then it's just going down, then it settles back down to a point. So it actually gives you a little bit more zero crossing. Where you're at that zero crossing, if you have something, some of these signals, they go up and they go down, and they kind of blip up and they go do that. You've seen that. That capacitor will jam the set point up a little higher and then come back down. It works, but the problem with that is at high RPM, this spreads out further. So you have to be careful with the capacitor you pick. Okay, but that's yet another fix. All right, and that's it for this. Questions? No, because it's across the point that you're doing where you're triggering, and it's only at it's changing the threshold. It will change a little bit your zero crossing. It will do it, so it can introducely do it. But at high RPMs, you got 70 volts. Your slope is so large. If this is 70 volts, you would just hit 0, and now you're at 5 volts. It doesn't matter. At lower RPMs, you have this. And if I have a large train, I have the absolute position changes. But you have a long time to do this here. The capacitor has bled down before the time has come back. At a higher RPM, you've got a bigger, higher signal. Slope is dramatic. So you're not going to see so much of a time. That's an excellent question. So you understand what's going on. Everybody's dead, aren't they? Okay. Huh? Good.